drift through the quiet story of mathematics, from ancient symbols to cosmic equations. Let numbers guide you gently to rest. Welcome to the Midnight Thinker, the dawn of numbers. Before cities, before writing, before history was written down, there were numbers. The story of mathematics begins not in libraries or laboratories, but in the wild, among hunter-gatherers who roamed the land, tracking the seasons, watching the skies, and counting the days. Long before agriculture or writing, humans had to reckon with patterns, the phases of the moon, the migration of animals, the changing weather. To survive, they began to count. One of the oldest known mathematical artifacts is a small piece of bone, no more than 10 centimeters long. Discovered in the 1960s near the headwaters of the Nile in present-day Congo, the Ishango bone is estimated to be over 20,000 years old. Carved into its surface are a series of notches arranged in deliberate groupings. Some believe these marks represent a lunar calendar. Others say they hint at an understanding of prime numbers. Whatever the case, this is not random scratching. This is intentional thought, the beginning of numerical abstraction. Meanwhile, halfway across the world, other cultures were independently developing their own systems of counting. In what is now modern-day Iraq, the Sumerians of Mesopotamia flourished around 3000 BCE. Living in the cradle of civilization, they developed cuneiform writing, pressing wedge-shaped symbols into clay tablets. Among the first things they recorded were numbers, the quantities of grain harvested, livestock owned, labor distributed. Their base 60 system, sexagesimal, might seem alien today, but we still feel its influence. 60 seconds in a minute, 360 degrees in a circle. They even had early multiplication tables, square root algorithms, and astronomical data, all preserved in hardened clay. Some of the oldest math problems ever recorded are word problems scratched into these tablets. If a man buys a field and pays 10 shekels for every square cubit, how many shekels does he pay for a field 12 cubits long and 10 cubits wide? These are not just arithmetic drills. They're glimpses into the daily lives and real-world applications of ancient people. To the west, in the Nile Valley, the ancient Egyptians were developing their own brand of mathematics, practical and deeply tied to survival. Every year, the Nile would flood, washing away the markers of property boundaries. And every year, the Egyptians would recalculate and remeasure using their unique unit, the cubit, along with ropes and tools to re-establish the land. Thus was born geometry, literally, the measurement of the earth. The pyramids, symbols of divine order and human ambition, were impossible without a solid grasp of mathematical proportion. The builders used a system of unit fractions, like 1/2, 1/3, 1/4, and they encoded mathematical problems into their papyri, the Rhind mathematical papyrus and the Moscow papyrus, which contain calculations for the volume of a pyramid, rules for dividing food among workers, and even algebraic puzzles. But even before writing, numbers may have been linked to something more spiritual. Across Africa and Europe, archaeological sites suggest that early humans associated counting with celestial movements and fertility cycles. Some ancient tally marks found in caves matched the number of days in a moon cycle, suggesting that early mathematics was also tied to timekeeping, ritual, and belief. Half a world away, The Maya civilization in Mesoamerica developed an advanced mathematical system based on 20, a vigesimal system, likely inspired by counting on fingers and toes. They conceptualized zero independently, centuries before it arrived in Europe, and used it in calculations as early as the 4th century. Their base 20 system allowed them to predict eclipses, chart the movements of Venus, and design massive calendar cycles like the Long Count, which tracked time over spans of thousands of years. Sadly, most of these were burned during the Spanish conquest, one of the greatest cultural losses in mathematical history. These early systems, from Africa to Mesopotamia, Egypt to Mesoamerica, demonstrate one powerful truth. Mathematics is not a Western invention. It is a human invention. It arose in every corner of the earth where people observed, recorded, and tried to understand their world. They counted not just to trade and build, but to understand the universe, to ritualize time, and to leave something behind. Or there was philosophy before science, before language even found its full form. There were numbers, and from those numbers, civilization began to count the stars, the steps, the seasons, and itself. Greek genius and the birth of proof. The ancient world was full of practical math. Farmers measured fields, merchants calculated trade, priests tracked the heavens. But it was in ancient Greece that mathematics became something more, an art, a science, and a way of seeing the world. It began not with numbers, but with shapes. Around 600 BCE, a man from the island of Samos named Thales made a revolutionary claim that nature followed rules, and those rules could be discovered through reason. Thales is often credited with bringing Egyptian geometry to Greece. But instead of using it only to measure pyramids or fields, he began asking deeper questions. If two lines intersect, what is the relationship between the angles? What makes a triangle similar to another? With Thales, geometry was no longer just a tool. It became a language of truth. But it was one of Thales's students who would light the flame of mathematical legacy, Pythagoras. To modern ears, Pythagoras is mostly remembered for one thing: a squared plus b squared equals c squared, the Pythagorean theorem. But the real story is far stranger and more profound. The followers of Pythagoras were more than mathematicians. They were mystics. They believed the universe was built on harmony, and that harmony could be found in number. They studied the ratios in music, plucking strings to discover that having the length doubled the pitch. To them, this wasn't just math. It was the structure of the cosmos. They believed that mathematics was divine. Yet their discoveries led to a crisis. The Pythagoreans discovered that not all quantities could be expressed as ratios. Take the diagonal of a square with sides of length 1. According to their theorem, its length is the square root of 2. But square root of 2 cannot be written as a fraction. It is irrational, a number that defied their belief in perfect ratios. Legend says the discovery was so dangerous, one Pythagorean who revealed it was drowned for speaking it aloud. Whether true or not, this moment marked a turning point. Math was no longer just spiritual. It was complex, paradoxical, even unsettling. The golden age of Greek mathematics would come with Euclid, around 300 BCE in Alexandria, Egypt, a city that had become the intellectual capital of the Mediterranean. Euclid wrote The Elements, a 13-book compilation that would become the most influential textbook in history. It began with just 5 axioms, simple truths assumed to be self-evident, and built an entire universe of logical proofs from them. From triangles and circles to number theory, Euclid showed that mathematics could be deduced step by step from first principles. This was math as a deductive science. It influenced everyone from Islamic scholars to Newton, even Einstein, 2,000 years later. But Greek math didn't stop at geometry. Enter Archimedes, the mathematical genius of Syracuse. Archimedes invented early calculus-like methods, calculating the area under curves and the volume of spheres and cylinders. He approximated pi with stunning accuracy and invented clever mechanical devices, including war machines to defend his city. His last words, as Roman soldiers broke into his home, were said to be, "Do not disturb my circles." A mathematician to the end. There were others too. Eratosthenes, who measured the circumference of the earth using shadows and sticks. Hipparchus, who laid the groundwork for trigonometry. And Apollonius, who explored conic sections, laying a path that would eventually help launch rockets and satellites. Greek mathematics was a leap, not just forward in knowledge, but in philosophy. For the Greeks, math wasn't just useful, it was beautiful. It revealed an underlying order in the universe, a hidden structure to reality. And though Greek civilization would eventually fade, these ideas, the power of logic, the beauty of proof, and the mystery of the infinite, would survive, waiting to be rediscovered in the patterns of the stars, in the lines of a triangle, in the song of a vibrating string. The Greeks saw something eternal. And in doing so, they helped mankind begin to see the invisible. The age of calculation, India, Islam, and the invention of zero. A new mathematical fire was kindled thousands of kilometers east, in the lands of India and the Islamic caliphates. Here, mathematics evolved not only as a philosophical pursuit, but as a practical necessity for astronomy, commerce, religious rituals, and navigation. But something extraordinary happened during this time. The invention of a concept so simple and yet so revolutionary that it would forever change the course of human thought. That idea was zero. In ancient India, numbers had always played a sacred role. From Vedic chants to astronomical tables, counting and calculation were deeply woven into culture and religion. But it was in the 5th century CE that an Indian mathematician named Aryabhata made a leap. In his treatise Aryabhatiya, he introduced a system where the place of a digit mattered, a positional decimal system. Though he used words instead of symbols for digits, this was a monumental shift. It allowed numbers to stretch beyond boundaries. You could now express millions using just a few digits. Then came Brahmagupta, around 628 CE, who did something no one had dared. He gave zero a name, Shunya, the void. But more than that, he gave it rules. If zero is added to a number or subtracted from a number, the number remains unchanged. A number multiplied by zero becomes zero. This was not just symbolism. It was the birth of abstract number theory. Zero became a placeholder and a number in its own right. With zero came negative numbers, debt and deficit, and even algebraic reasoning. While Europe lingered in the shadows of antiquity, the torch of mathematical knowledge was passed eastward and then westward. to the Islamic Golden Age. In the 8th century, the city of Baghdad became the epicenter of intellectual fusion. Here, under the Abbasid Caliphate, Greek, Indian, Persian, and Babylonian knowledge was translated, preserved, and most importantly, expanded. It was here that al-Khwarizmi, a Persian scholar, wrote Kitab al-Jabr wal-Muqabala, the book of completion and balancing. From this title, we get the word algebra. Al-Khwarizmi didn't just solve equations, he formalized the process of solving them. He treated unknowns like real entities, using systematic methods to move them around an equation. His work introduced the idea of algorithms, a term that comes from the Latinized version of his name. This was mathematics as procedure, step-by-step logic, the very foundation of computer science centuries ahead of time. Other Islamic scholars carried the torch even further. Omar Khayyam, known today for poetry, developed a powerful classification of cubic equations. Al-Tusi advanced trigonometry, making it a field of study independent from astronomy. Al-Biruni calculated the radius of the Earth with amazing precision, using nothing but shadows and trigonometry. And Al-Kashi, in the 15th century, calculated pi to 16 decimal places, using only pen and paper. They refined the sine, cosine, and tangent tables. They applied math to map the stars, determine prayer times, and lay out compass directions for mosques across continents. One of the most stunning achievements of this era was the preservation and translation of knowledge. Greek works like Euclid's Elements and Ptolemy's Almagest were translated into Arabic and extended. These scholars didn't merely copy, they critiqued, corrected, and improved. They created observatories, calculated planetary orbits, and helped lay the groundwork for modern science. The influence of Indian and Islamic mathematics spread westward through Spain, North Africa, and the Silk Road, eventually reaching medieval Europe, where a young man from Pisa named Leonardo Fibonacci would introduce these ideas to the Latin world. Fibonacci's Liber Abaci, published in 1202, promoted the Hindu-Arabic numeral system, the one we use today. With it came zero, positional notation, and easy arithmetic, replacing the cumbersome Roman numerals. It was the start of a revolution. The legacy of Indian and Islamic mathematicians is vast. The invention of zero, the birth of algebra and algorithms, the systematization of trigonometry, the refinement of decimal systems. Without these, modern science, engineering, and technology would be impossible. They built the bridges centuries before Newton and Leibniz would cross them. In the space between stars and symbols, in the silence of zero, ancient minds dreamed of infinity and changed the world forever. The Age of Proof, Europe's mathematical renaissance. As Europe emerged from the long shadow of the Middle Ages, a spark of curiosity reignited the Western world. It began in art, philosophy, and science. But deep within it all was the rise of something far more fundamental, the rebirth of mathematics. This was the Renaissance, and with it came a dramatic shift. Mathematics was no longer just a tool for merchants and astronomers. It was becoming a language of the universe. In the 1400s, Italian polymaths like Leonardo da Vinci explored the harmony between math and nature. To Leonardo, mathematics was not abstract. It was the blueprint of life itself. He used geometry to understand anatomy, architecture, and motion. But it was in the 16th century that mathematics would undergo its true revolution. Enter Niccolò Tartaglia, Girolamo Cardano, and Lodovico Ferrari, a trio that cracked open the mystery of cubic equations. For centuries, mathematicians struggled with equations like x to the power of 3 plus x equals bi. No general solution was known. But in a dramatic series of mathematical duels, yes, public math battles were a real thing, these men revealed the first algebraic solutions to cubic and quartic equations. The work, published by Cardano in his book Ars Magna, marked a seismic moment in algebra's history. But there was a twist. Their solutions sometimes involved the square roots of negative numbers, which didn't make sense at the time. Mathematicians called them imaginary numbers, a name that stuck, even as they would go on to power modern electronics and quantum theory. The next leap came from a brilliant and enigmatic figure, Pierre de Fermat. A lawyer by trade, he pursued mathematics in his spare time. And in the margin of his copy of Arithmetica, he scribbled, "I have discovered a truly marvelous proof of this, which this margin is too narrow to contain." That innocent note became Fermat's last theorem, unsolved for over 350 years. It was a challenge to the world. No three positive integers a, b, and c satisfy the equation a to the power of n plus b to the power of n equals c to the power of n for any integer n greater than 2. This unsolved mystery would torment and inspire generations. But Fermat's influence didn't stop there. He helped invent analytic geometry and laid the groundwork for calculus. Meanwhile, in England, another towering figure was rising. Isaac Newton, born in 1642, changed everything. In a time of plague and personal isolation, he conceived one of the most powerful ideas in human history: calculus. Working in secret, Newton developed a system to understand motion, acceleration, and change. Using limits, infinitesimals, and derivatives, he gave the world the ability to model the physical universe with astonishing accuracy. At the same time, in Germany, Gottfried Wilhelm Leibniz independently developed his own version of calculus. His notation, like fraction dy dx, is still used today. Though a bitter rivalry erupted between their supporters, both men had reshaped the very fabric of mathematics. Without calculus, there would be no engineering, no physics, no space travel. With calculus, the universe was no longer a mystery. It was a machine, and mathematics was the code that made it run. This age of proof didn't just answer old questions, it dared to ask new ones. René Descartes bridged algebra and geometry, turning curves into equations. His Cartesian plane made it possible to graph the unknown. Every graph you've ever drawn, every function plotted in school, owes its existence to Descartes. Blaise Pascal pioneered probability theory, originally to solve gambling problems. But it became the bedrock of statistics, risk analysis, and data science. Mathematics was no longer a servant to philosophy. It was its own force, a discipline of rigor and logic. And as Newton's laws predicted the motion of planets, tides, and cannonballs, humanity began to see the world with fresh eyes. It was not ruled by gods or chaos, but by elegant laws, written in equations. The Renaissance gave us perspective. The Enlightenment gave us precision. And mathematics? It had become the language of nature itself. The infinity problem, madness, genius, and the edge of logic. What is infinity? It's a question that's haunted the minds of mathematicians and philosophers for centuries. Endless, boundless, a concept so simple a child could imagine it, and yet so complex, it nearly broke the minds of those who dared to define it. Welcome to the 19th century, where mathematics stood at the brink of the unknowable, and where the fight to understand infinity would push some of the greatest minds into brilliance, and others into madness. Georg Cantor, a German mathematician born in 1845, was obsessed with the idea of the infinite, not just as a vague idea, but as something that could be measured, categorized, understood. What he discovered would revolutionize mathematics and shatter its foundations. Cantor showed that there's more than one kind of infinity. That may sound impossible, but here's how it works. Take the set of natural numbers, 1, 2, 3, 4. That's infinite, right? Sure, but now, take the set of real numbers between 0 and 1. That's also infinite, but it turns out it's a bigger infinity. Cantor's diagonal argument proved that no matter how you try to list the real numbers, there will always be one you missed. He defined the sizes of infinity using symbols like Aleph Null, the smallest infinity. This wasn't just groundbreaking, it was terrifying to the mathematical world. Some contemporaries accused Cantor of heresy. Others said he was mentally unwell. Even the legendary Henri Poincaré called his work a grave disease infecting mathematics. And yet, Cantor's ideas would eventually become the cornerstone of modern set theory and the very basis of how we understand mathematical structures today. But the rabbit hole went deeper. In the early 20th century, mathematicians sought to clean up the foundations of math. They wanted to build a system where everything could be proven from first principles, a kind of perfect logic machine. Enter David Hilbert. In 1900, he announced a list of 23 unsolved problems in mathematics, a kind of roadmap for the future. One of them asked, "Can all mathematical truths be proven logically from a set of axioms?" This would become the central question of 20th century mathematics. But the answer would come with a devastating blow. Kurt Gödel, a soft-spoken, deeply introverted genius, found the crack in the foundation. In 1931, Gödel published his incompleteness theorems. The gist? In any consistent mathematical system, there are truths that cannot be proven within the system itself. Let that sink in. He proved that mathematics is incomplete. There will always be true statements that cannot be proven. Logic cannot prove everything. Gödel had placed limits on human knowledge, and the cost was heavy. He became increasingly paranoid, isolated. Later in life, he believed he was being poisoned and would only eat food prepared by his wife. When she was hospitalized, he stopped eating altogether and died of starvation. Infinity, logic, paradox. They weren't just ideas. They were the battlegrounds of the mind. And yet, out of that struggle came tremendous beauty. From Cantor's infinities to Gödel's limits, we learned a hard truth. Mathematics is not a perfect machine. It is a reflection of ourselves, beautiful, flawed, and infinite. The age of certainty was over, but in its place, a new era had begun, one where abstraction could unlock new dimensions, where numbers could mean anything, even nothing at all. And that brings us to the strangest century yet, a time where mathematics would leave paper behind and enter the world of machines. into the abstract, from geometry to machines. By the dawn of the 20th century, mathematics had traveled from the ancient sands of Egypt to the chalkboards of Europe. But as the century progressed, math began to transform, no longer tied strictly to shapes, quantities, or the physical world. This was the age of abstraction, where numbers broke free from the need to represent anything and became powerful tools in their own right. It was also the age where mathematics would begin to speak to machines, not just numbers on paper, but logic that powered the digital revolution. At the forefront of this new era was abstract algebra, a language of structures. Instead of simply solving equations, mathematicians like Évariste Galois asked, what are the rules that govern equations themselves? Galois, a brilliant but tragic young mathematician, laid the foundations of what we now call group theory. He realized that the solutions to polynomial equations were governed by symmetries, abstract structures that could be manipulated like puzzles. The implications were stunning. Galois' work explained why some equations could be solved and others, like the quintic, simply couldn't. He died in a duel at age 20, leaving behind scribbled notes and the birth of modern algebra. While algebra soared into abstraction, geometry was undergoing its own revolution. For centuries, Euclidean geometry, the familiar world of points, lines, and planes, was the gold standard. But mathematicians began to wonder, what if space itself bent? This led to non-Euclidean geometry, where parallel lines could meet, and the angles of a triangle didn't always add up to 180 degrees. At first, these strange ideas seemed like mathematical fiction. But then came Albert Einstein. With his theory of general relativity, Einstein used Riemannian geometry, a curved space model developed by Bernhard Riemann, to describe gravity not as a force, but as a warping of space-time. Math wasn't just a tool for science anymore. It was the architecture of reality. And then came the machines. Alan Turing, a British mathematician and logician, asked a daring question. Can thought be mechanized? To explore this, he created the Turing machine, a theoretical device that could simulate any computation. It was the birth of computer science and the idea behind every modern processor. Turing's work led directly to the development of early computers, and his code breaking during World War II helped defeat the Nazis. But his genius was not celebrated in his time. He was persecuted for his sexuality, forced into chemical castration, and died under tragic circumstances in 1954. Today, Turing is considered one of the fathers of artificial intelligence, and the Turing test, used to evaluate a machine's ability to exhibit human-like intelligence, bears his name. The 20th century gave rise to entire new fields of mathematics. Topology, the study of space, and connectedness, where a coffee cup and a donut are mathematically identical. Category theory, called mathematics of mathematics, which finds common structures across vastly different fields. Chaos theory, which shows how deterministic systems can still behave unpredictably. A butterfly flaps its wings in Brazil and causes a tornado in Texas, and perhaps most powerful of all, mathematical logic, which shaped how we build software, encrypt messages, and automate decisions. With mathematics, we built the digital world. Every algorithm, every line of code, every pixel, password, and post made possible by mathematical abstractions. And as computers grew more powerful, so did the math. From linear algebra powering 3D graphics, to graph theory enabling social networks, to Fourier transforms making video and sound compression possible, math became invisible infrastructure. The world as we know it now runs on algorithms, on calculus, number theory, logic, on equations once scribbled in isolation that now shape entire civilizations. From the abstract to the applied, from the infinite to the automated, mathematics had not just explained the universe, it had begun to build new ones. Crisis and creativity in the 20th century. The 20th century, a time of upheaval, revolution, and unimaginable discovery. A time when the certainty of mathematics itself was shaken to its core. What happens when the foundations of truth crack? This is the story of crisis and creativity, of minds that questioned everything and built something new. In 1931, a 25-year-old logician named Kurt Gödel dropped a bombshell on the mathematical world. His incompleteness theorems proved something terrifying. In any sufficiently powerful mathematical system, there will always be statements that are true but cannot be proven. It shattered the dream of a complete, consistent, and all-encompassing mathematics, a dream that had guided thinkers like Hilbert and Frege. Mathematics, it turned out, could never prove all truths. There would always be mystery. But from that crisis came creation. Just 5 years later, Alan Turing introduced the concept of the universal machine, what we now call a computer. With it, he invented computer science, showing how logic could drive machines. Turing's work laid the foundation for the digital age and posed profound questions about intelligence, computation, and even consciousness. Meanwhile, in physics, mathematics helped unlock relativity and quantum mechanics, the deepest descriptions of the universe. Einstein's equations of general relativity reshaped our view of space and time. But it was the strange, probabilistic world of quantum theory that shook our understanding even more. Here, math no longer described certainty, but probability, entanglement, and superposition. Was reality itself uncertain? It wasn't just the universe that got stranger, mathematics did too. New branches emerged. Topology, the mathematics of shape and deformation. Fractal geometry, pioneered by Benoit Mandelbrot, revealing patterns in nature, clouds, coastlines, lungs. Chaos theory, showing how small changes can lead to wildly different outcomes, a butterfly's wing, a hurricane. And the faces of mathematics began to change. Emmy Noether revolutionized symmetry and physics. Mary Cartwright, David Blackwell, Julia Robinson, and others pushed boundaries in math and in society. The 20th century was not just about problems, it was about progress. Out of its crises came bold new creativity. Mathematics had survived its greatest test, not by retreating into certainty, but by embracing uncertainty and discovering new beauty in the unknown. The hardest equations ever solved. Some equations are simple, some are elegant, and then some are monsters. Equations that take decades to solve, equations that resist every attack, equations that drive mathematicians to obsession. This is a journey through the Mount Everests of math, the hardest equations ever solved. In 1637, Pierre de Fermat scribbled a note in the margin of a book. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. The problem? No three positive integers a, b, c can satisfy the equation a to the power of n plus b to the power of n equals c to the power of n for any n greater than 2. For over 350 years, no one could prove it, until 1994, when Andrew Wiles, after 7 years of secrecy and solitude, cracked the code using modern tools Fermat never dreamed of: elliptic curves and modular forms, a centuries-old puzzle solved by connecting distant branches of math. Seems simple. Any map can be colored with just 4 colors, so that no neighboring regions share a color. Obvious, right? But it took over a century to prove, and when it was finally done in 1976, it was controversial. The proof required a computer, thousands of cases. No human could check them all. It marked the dawn of a new age, math done with machines. Fluid motion, water, air, fire. The Navier-Stokes equations describe them all. And yet, nobody can prove whether smooth solutions always exist. It's one of the clay millennium problems, and one of the most important, with implications for weather prediction, aerodynamics, and more. Can we understand the motion of the sea with math? So far, no. At the heart of prime numbers lies the Riemann zeta function, a strange and beautiful object. The Riemann hypothesis claims that all its non-trivial zeros lie on a specific line in the complex plane. No one has proven it, but if it's true, it holds the key to the pattern of primes, cryptography, and possibly more. Billions of calculations support it, but no proof. Not yet. Quantum field theory works. It predicts particles. It powers the Standard Model, but we don't know why it works. Mathematically, it's not proven. The Yang-Mills equations, another millennium problem, ask for a rigorous explanation of how mass appears in quantum fields. Physicists use it every day, but no one can prove it. In modern math, we can use equations, even when we don't fully understand them. Some equations remain unsolved, some maybe always will. But the effort to solve them has led to deeper truths, better tools, and even new mathematics itself. The hardest equations are not obstacles. They are doorways to something greater. The future of math, frontiers, AI, and the unknown. Where do we go from here? After thousands of years, through pyramids, paradoxes, proofs, and processors, mathematics has brought us to the edge of knowledge, and now it's poised to take us beyond. Welcome to the future of mathematics, where the frontier isn't just equations on paper, but the unknown itself. Today, some of the biggest breakthroughs in science and technology are powered not just by math, but by mathematics we don't fully understand yet. One of the most exciting and unsettling developments is the rise of artificial intelligence. With algorithms built on linear algebra, calculus, probability, and optimization, machine learning systems can now write music, design molecules, and beat humans at the most complex strategy games ever invented. In 2016, AlphaGo, a deep learning AI built by DeepMind, defeated world champion Lee Sedol in the ancient game of Go, a game once thought too complex for machines. What surprised mathematicians wasn't just that AlphaGo won, it was how it played. It made moves no human ever had. Moves that looked irrational, until they turned out to be brilliant. Are we witnessing machines discovering new mathematics? And yet, many of the greatest mathematical mysteries remain unsolved. The Riemann hypothesis, the key to understanding the distribution of prime numbers, and possibly the deepest question in number theory. The Navier-Stokes equations, which govern fluid motion and could unlock a better understanding of weather, blood flow, and the stars. The P versus NP problem, which asks, can every problem whose solution can be verified quickly also be solved quickly? These are just some of the Millennium Prize problems, 7 unsolved puzzles, each worth $1 million, and more than that, immortality. Only one has been solved so far. The rest remain open, waiting. We're entering an era where computation and theory merge like never before. Quantum computing, rooted in the strange math of quantum mechanics, promises to break encryption and simulate molecules with terrifying power. Homotopy-type theory reimagines the very foundations of mathematics, blending logic with geometry. And experimental mathematics uses brute force computer searches to find new patterns the human eye can't detect. Some researchers now speculate that AI could one day generate entirely new branches of mathematics, structures never imagined by humans. But would we even understand them? Would we become students of our own creations? Still, the heart of mathematics isn't in supercomputers or grand equations. It's in the human desire to understand, to explore, to ask why and what if. From the first time a child counts on their fingers, to the moment a physicist glimpses a new dimension, mathematics is a language of curiosity, a map of what we know and what we dare to imagine. As we move into the future, the greatest equations may still be waiting to be written, the deepest truths still waiting to be discovered, because math is not finished. It never will be. And maybe that's the most beautiful equation of all.